everybody. Thank you for joining the Synthetic Intelligence Forum. My name is Vic. I'm the founder of the Synthetic Intelligence Forum. And today it's my pleasure to welcome Dr. Pooya Ronagh to the forum to talk about advances in quantum machine learning. Dr. Ronagh, it's a pleasure for me to have you join us today. Thank you for taking the time to meet with us. And you have picked a very interesting topic, which is very near and dear to the hearts of our community members, many of whom specialize in data science, artificial intelligence, and machine learning, and are very curious to know about where the world of quantum overlaps and where the synergies and the value can be really amplified and magnified. So without further ado, I'll share your screens and please take it away.
Thanks so much, Vic, for the introduction and for the invitation. And thanks to the audience for joining. And I hope that you like both the topic and the subjects that I've selected to discuss today. So yes, Vic asked me to talk about quantum machine learning, and that's kind of the field that I'm working in my own research and R&D on. And so I will be selecting things that are closer to my own research interest. The field is pretty broad. There's a big community of my colleagues that are working on quantum machine learning, quantum machine intelligence, in quantum information processing. So I will try to both give you a broad view of what are the different flavors of the field and what are the different types of works that are happening in the community about it. But also then, kind of motivate where things stand from my own research and the work in progress that I have with the lab at 1QBit and my students at the University of Waterloo. Okay, so I want to step back a little bit and ask, what makes an algorithm be intelligent, or what does it mean to develop a machine learning scheme as opposed to other algorithms? So we develop a lot of algorithms in computer science, and some of them are considered intelligent, some of them are not intelligent necessarily. And intelligence doesn't necessarily mean efficiency. They're not equivalent to each other. So I think this is, I would assume that this is a good folklore definition for an intelligent system or an algorithm that learns. So what does it mean to learn? I broadly say learning from data, but data would mean, it could be interaction of an intelligent agent with its environment. So you collect data from your different ways of sensing or different ways of interacting with the environment and changing the state of the environment. All of that I kind of, broadly talk about it as data. But, data could really also be a data set, or, like lines and lines of numbers in a spreadsheet, or a data set of images, or a data set of texts gathered from, newspapers or books, and you want to do either some vision, image processing task on it, or things like natural language processing. All of them or you're you have an agent that is interacting with the environment in a setup like reinforcement learning. In all those cases, I will talk about the information gathered by the system as data. Okay, so an algorithm is said to learn from data if its performance improves by the result of inspecting more data points. So I think that's a nice differentiating factor between lots of algorithms that are very, very efficient in the tasks that they're doing, but they're not learning from the data that they're receiving in their inputs. So, for example, as a simple example, sorting algorithms, any sorts of bubble sort, quick sort, merge sort, all these things that we learn in computer science classes, they're not intelligent. There are also quantum algorithms that are not learning, or they're not intelligent. For example, quantum algorithm for searching, for sorting in unsorted data list, element distinctness. These are not intelligent, and so it's not a matter of being a classical algorithm or a quantum algorithm. It's that the performance is known, you can study it, and the performance does not change by rerunning the algorithm over more instances of its inputs. Okay, so machine learning is very important for decision-making scenarios, like face and voice recognition in smartphones. All of it is happening using machine learning today. However, state of the art falls short of reliable decision-making agents that can be deployed, safely and securely in sensitive decision-making scenarios such as surveillance, security, other places that the things are, even more critical. The decision is more critical than unlocking a device, for example. Okay, so all of these advancements that have happened in machine learning, they're broadly done through a method that is known as deep learning. And I will specifically want to show this diagram that, what we kind of, especially in kind of the public forums in science and technology, these terms are considered quite equivalent to each other. AI, ML, and deep learning, but really, actually, if I look at the places where we have the most applications today, most of it is falling under deep learning. But deep learning is only a umbrella is a subset of the umbrella of methods that are considered under machine learning. And then machine learning itself is a subset of things that are generally broadly talked about as making a machine be intelligent. So that's called AI. And what you mean by intelligence is it could be way beyond what is written in this definition that I was showing here, because you could be asking for the agent to simulate consciousness. Or simulate a biological intelligence system, a biological neural system. And those are like beyond what is in the umbrella of machine learning. Okay. In fact, by the way, it's true that deep learning has been very successful, but also a lot of the computational foundations of it, why does it succeed in places and why does it fail in other places, is a hot topic of research in current scientific communities. And that, I think, is a good motivation for looking at other computing paradigms for achieving intelligent systems. Okay, so a little more technical jargon here. So a machine learning model is a parametrized probabilistic graphical model. So what does that mean? A graphical model is this picture that we always see from, again, like AI forums that you see, like, AI has unlocked certain applications. You see this graph of nodes, and there are connections between the nodes. And the explanation is that those nodes resemble neurons in a biological nervous system. And the connections between them is these synapses that make the neurons react to the activations of each other. And that creates a graph, right? So that graph is called a graphical model, a little lengthier probabilistic graphical model. And the fact that you have the choice of that graph lets you decide how strongly each neuron is affecting its nearby neurons, is this parametrization. So the amount of that is these weights and biases that are trained in a machine learning algorithm, and that's why it's a parametrized graphical model. Okay, and then there is a notion of a model distribution, and a model distribution is our way of understanding how to train these models is usually using probability and statistics. And the way we do it is we take this graphical model, we associate a distribution, which we call model distribution. And the model distribution is supposed to have features. It's supposed to be a probability distribution that is not specific to any single input of your training data set, right? So it's canonical in a sense, independent of any particular choice of inputs and outputs to your deep learning scheme. As soon as you talk about something like a canonical distribution, notions from statistical physics, statistical mechanics come into play, and you might already know that, like, for example, training neural networks is done using things like cross entropy loss functions, entropy of information becomes an important concept. So all of these are concepts that were originated in understanding ensembles of particles in statistical physics, and then they made it to the machine learning jargon. Okay, so then there is this second piece, which is the training. And training is a method it's the scheme, an algorithm, that starts from some choice of these parameterization, how strongly these neurons are interacting with each other. And then you have a method of showing more training data to your agent. For example, it's supposed to see pictures of dogs and cats and then be able to distinguish them by labeling them dogs versus cats. In that situation, this prediction is called a classification task. And in a classification task, you start with some choice of these parameterizations, and they're maybe completely randomly initialized in the beginning. And your agent is not performant in distinguishing pictures of cats and dogs. But then your training scheme is going to change these parameters slowly to some optimal or suboptimal choice of parameters that then we say we have a trained network, and that trained network, if we show it an unseen picture of a dog versus cat, then in that inference mode, it's able to recognize the two labels from each other. Okay, so obviously it's important for this optimization, this is an optimization scheme. You have a notion of performance, like for example, how good you predicted dogs versus cats. And then you want to get to a better and better prediction accuracy in that task. So this is by nature, naturally it's an optimization problem to solve. And then what we want is for that optimization problem to be tractable, because it doesn't matter that in principle there is some choice of weights and biases in your network that can achieve certain performance, but it's also important to be able to efficiently find that choice. Okay, so this problem of making the training be tractable is quite critical, and that's where the places where there are roadblocks for deep learning, for example, show itself. So the fact that you have this likelihood of your model distribution and the distribution that you think your data set is coming from, usually we use some sort of likelihood. It's a notion of how two distributions are getting close to each other or not. So there's a distribution that the data set came from. There's a distribution that is the model distribution, and we want to make these two get closer and closer to each other. And that's the optimization problem we're trying to solve. The fact that you want that notion of objective function, this loss function, to be easy to compute and easy to train, creates a lot of limitations for your scheme. So the fact that you're asking for tractable likelihood means that is equivalent to asking for a tractable training procedure or tractable synthesis of pseudodata, like in inference mode, for example. And this is the place where you have to make a lot of engineering decisions on how you build that graphical model in the beginning so that you do actually end up with a tractable scheme. Okay, so now I'll switch gears. So this was just kind of a background on machine learning, and now we'll talk about what is quantum machine learning. So there are two things that I talked about. One is the machine, the model, or the agent, and then there's data, or that environment that I said the agent is interacting with. And whether these two, like the physics, the underlying physics of both of these creatures, will decide, what kind of world are we trying to be intelligent in. So you will see charts like this drawn a lot in surveys on quantum machine learning. And on one axis, you're talking about, the machine, the agent, the bot, the algorithm. And then on the other hand, you are distinguishing between classical and quantum for the data or that environment that the agent is interacting in. So if the machine is classical and data is classical, we get our good old conventional machine learning, which has been very successful in many applications, and it has had a lot of technological impacts in the past decade. Okay, so then there's a scenario where the machine is classical, but the environment or data is quantum. And that is already very well explored in the past few years in the quantum information processing community. And this usually has the flavor of we're trying to solve a problem about quantum physics, but we're going to use classical machine learning to achieve that. So, for example, I would say the field kind of really ramped up with this paper from 2018 on neural network quantum state tomography. So in quantum experiments, we build a quantum state using a lab experiment in the lab, and then we want to study that quantum state. For example, a quantum state of a molecule is an interesting thing from applications perspective to understand. Quantum states of qubits on a hardware device, after you run a certain circuit on it, is an interesting state of that device, the physics of that device that we want to understand. And because quantum measurements collapse quantum wave function into classical answers to the questions you're asking from the system, so you want to understand, see the quantum state from a certain angle, and that angle is something that in physics we call measurement axis. And that measurement axis, when you do your measurement in that particular axis or in that basis, you will get a classical bit as an answer. So 0 or 1. Like, for example, it's spin, and you get a spin up or spin down for the system. Okay, this transition from quantum state to classical bits gives you a very, very slow rate of learning about that quantum state. And this is one of the problems that using quantum mechanics to do computation or information processing in other quantum technologies, quantum sensing, broadly talking about quantum communication, all of them, the fact that measurement has this collapsible wave function naturally in it, and like physically in it, makes it hard to understand what state you study the state. So using a neural network to capture a classical neural network to capture a classical kind of snapshot of that quantum state, it would be very appealing, because then I can use the classical neural network to do other things with it, as you do in classical machine learning. And so this was the motivation for building this neural network quantum state tomography. And there are lots of good, even theoretical results, very strong theoretical results of this being a scheme that can work really well. So these theoretical advancements were way more recent. So we actually know that we can do this kind of task with certain notion of efficiency. I have worked in this area of using classical machine learning for quantum reasons in different places. For example, I've studied using reinforcement learning, classical reinforcement learning, to guide a quantum experiment. So you might know that reinforcement learning is a method for, you approximately do something like dynamic programming. So you have temporal decisions to make over time. And maybe those temporal decisions are decisions that you're going to make to derive a quantum system from certain, through an evolution. And so that's one of the things that I was very interested in. And I wrote this paper with Kyle Mills and Isaac Tamblyn. It was published in Nature Machine Intelligence. There's another preprint we have on a different flavor of similar type of application, which is also in publication order by the same journal, Nature Machine Intelligence, already accepted, and it's in publication order by Elizabeth Benevis, Florian Hoffmuller, Botan Kulczycki, and Juan Carrasquilla. So this last paper that I'm introducing here kind of started from where things were left off with neuron quantum state tomography, and we tried to find exactly what I said. So after you take this snapshot of the quantum state, then maybe you want to, for example, improve some of the statistics that you would have had to gather from this expensive, slow rate of quantum to classical information that you get from the measurements you do in the lab. But if I take the snapshot of the state, then I can manipulate that snapshot, which is a neural network, and maybe I can improve the statistics that I'm reading from it. So that's what we call neural error mitigation. Okay, so this kind of gets rid of this first row. So when the machine is classical, and the data is either classical or quantum in the sense of these publications. And so now the rest of this talk, I will talk about the case where the machine is quantum and the data is either classical or quantum. In fact, I will start talking about this box where the agent is quantum and the data is quantum first. And then I will end the lecture with the cases where the agent is quantum and the data is classical. Okay, so why do we like to build quantum computers? So quantum mechanics is a very successful theory that explains the quantum behavior of nature. But it has this computational crisis. So classical mechanics is very good at explaining classical features of the nature. For example, if you want to find the trajectory of a ball or a rocket or a plane, all of that is done by explanation through classical mechanics. And we can do computations with it. And that's very important because the fact that we can do computations allow us to build cars by simulation. So you don't, like when you're trying to build a new car, you don't keep building cars, testing, throwing them out, build a new car, test it through. You do that. Obviously, you prototype, but you do a lot of those early decisions of how you want the, like the aerodynamics of the car. You do all of that in simulation first. For example, when you're building a plane, by the time that the plane is getting to its tests, you're pretty confident that, it's going to fly and it's going to land safely. We're not doing, we're not crashing a lot of planes into the ground before we figure out how the wings have to look like. And the reason we can do that is because we can do computer simulation. So we can simulate the classical physics of these classical objects really, really precisely. And the fact that we can do all of that in silico lets us not end up in very expensive trial and error situations when we want to build something. Unfortunately, with things that we need to understand the quantum behavior of those systems, this is not the case. For example, building material with certain properties, chemical compounds, drugs, medicines that have certain behavior. All of this is done through lab experiments. So it's really like mainly driven by trial and error. And the reason that is the case is we actually know everything about the Schrodinger equation in that chemical compound. We just can't simulate, like we can't solve that Schrodinger equation. And that's quite frustrating. Like when you know exactly what's happening, but you can't compute, it's quite frustrating. And I think that frustration led physicists who, by the time that Feynman and others were proposing a quantum computer, they had already worked with quantum mechanics and they had developed the theory of quantum nature, quantum behavior of nature for decades, for 60, 70 years by that time. But this frustration that, once you get to just a little bigger than hydrogen molecule or lithium hydride molecule or water molecule, you just can't write down what the wave function looks like because it takes exponentially lots of memory. That was the reason that the scientists proposed that, well, maybe we actually have to build the computer in a way that is actually quantum. So if we want to simulate quantum behavior, we have to have a programmable quantum device so that we tell the device what Schrodinger equation to solve. Schrodinger equation is being solved in nature all the time. It's just it's not the equation we want. And so if the quantum device is programmable in a way that we solve the Schrodinger equation that we want at our will, and we ask the right questions from the solution, then you have this programmable quantum device, which is very different from tiny molecules that we don't have enough knobs to turn on them. Okay. this motivation hopefully is a good enough explanation to convince you that we can simulate quantum mechanics quite efficiently on a quantum computer. And from a technical jargon, this is called Hamiltonian simulation. And when I say we can do it really, really good, it means that the number of gates we have to use, like the number of instructions, quantum instructions we have to perform, is very good. The number of times we have to query the system, like gather data about that system, is very good. The precision of the solutions we make are very good. And these are proven through a sequence of theorems that I'm not writing all that development, but kind of the state of the art ended up in this theorem from Lau and Chuang at 2016 that they showed that basically doing this kind of Hamiltonian simulation can be done efficiently on a quantum computer. Okay, so, but the fact that we can do Hamiltonian simulation very well did have implications on things that looked like classical data processing. For example, solving a linear system. So you're given a matrix A and a column vector B, and then you're asking for a solution to the system AX equal to B, turns out to be an application of this Hamiltonian simulation. So there is nothing quantum happening in A and B, but you can turn, like, for example, you can make A be a block in something that looks like a quantum Hamiltonian, and then you use these Hamiltonian simulation schemes to then prepare in a quantum register what would have been the answer to this equation. Basically, you have a quantum register that then stores X as a quantum state, and I will explain what that means. So this was first done by Harrow, Hasidim, and Lloyd in 2009, and for a while it's still known as the HHL algorithm. But then there were lots of improvements on it. For example, the precision was improved later on in this publication from Ambanis and Childs and co-authors. And so because of that, I will call it the quantum linear system algorithm, QLSA. Okay, so it's quite like how fast can we solve linear? I mean, we solve linear systems all the time in classical computers. We use that as a building block for optimization, linear programming, finite difference methods, solving differential equations, fluid dynamics, all sorts of things. They use the solutions to linear systems all the time. But what was shown in these publications is that we can do this in a time that is logarithmic in dimensions of A and B, and that's quite impressive. That's an exponential speed up. Like if your matrix was n by n, you only spend log n time to prepare X in a quantum register. So that's very amazing, because then I can solve in polynomial time linear systems that are exponentially large. The dimensions, the number of equations and variables are exponentially large. Okay, I'll just skip this detail that the complexity doesn't just go away. It gets captured in a different place that's called the condition number of this matrix A. Okay, but then there are limitations. So for example, what does it even mean to take only logarithmic time to solve a linear system if I don't even expect the entries of A and B? I mean, if I were to just give you B by enumerating its entries B1, B2, and so on, I have to sweep at least one time over this column vector B, and that takes linear time in the dimension of B. But I told you that we can solve this system in logarithmic time in dimension of B. So one of these assumptions in this algorithm is that A and B were already kind of given to you in something like quantum memory. So if you're going to spend time to get A and B as input, as done in classical algorithms, then this exponential improvement evaporates. Same thing happens for X. If the algorithm is going to give you the answer X by showing you all its elements of this column vector X, then you don't get that exponential speed up. Okay, so, but then how can we use it? So it was studied with these assumptions that maybe we are in some setting where A and B are given, somehow prepared in quantum memory, and we don't actually want to know all of the entries of this solution, but maybe we want to ask a question about the solution. Then different applications were developed, and those applications are in the same flavor of classical applications of solving classical systems. So, for example, if you want to do something like signal processing, compressed sensing, to understand like the cross section of signals that are sent to a complex object, then you can do that by solving linear systems. So these are kind of inverse problems and linear inverse problems. And so you can imagine a setup where, for some reason A and B were somehow given to you in quantum memory, and then you want to solve a system like that for signal processing. If in solving differential equations, so this HHL paper was picked up very soon by Layton and Osborne, and then Berry, and the list is very long. So this field of solving differential equations using quantum linear system solvers is quite developed by now. Because the reason is, finite difference and finite element methods in classical computing also basically turn differential equations into very large linear systems that have to be solved. Okay, other type of places where you can, for example, when you're trying to find the minimum of a quadratic function, you can write that as you can actually write analytically what that is, and it's certain matrix multiplications, and then you can use a linear system solver to do the same task. Also, in machine learning, there are lots of places that you can turn your scheme, your machine learning, classical machine learning scheme, into solving linear systems. So quantum principal component analysis, supervised, unsupervised learning, support vector machines, all of them are places where if you could solve linear systems very efficiently, then you can expedite these algorithms. So this was picked up in 3 different publications by Lloyd, Mohseni, and Reventras. One of the ones that for a long while was considered as a very, very good application was this quantum recommender system. So that's the type of algorithm that, the old Netflix competition kind of motivated. And it's the, all the feeds that you have in social media, they kind of use recommender systems. So this linear system solver gave a what seemed to be an exponential speed up for solving, for developing a recommender system using a quantum computer. But as I said, the big limitation, which I didn't answer yet, is how am I even receiving data? So I said that data that represents A and B somehow have to be in quantum memory in some sense. But if you're starting from classical data and you have to prepare some quantum state with the data, then you're going to at least do some operation on each of your samples, and that will make this exponential speed up go away. And kind of the assumption in these papers is that you have access to something called a quantum variant of random access memory as it exists in classical computing architectures. And so that means that even if you could solve this problem of preparing these exponentially many data points in some efficient way in your quantum memory, the quantum memory itself is at least as large as the data set. And this exponential speed up is only useful when you use exponentially large data sets. So that means the quantum memory is exponentially large, which is not a good assumption. You kind of like went from, you made a trade-off between time and space, but you didn't really achieve a lot because you now have to worry about having exponentially large quantum memory. There are other problems with QRAM. For example, if you have exponentially many, what are called qubits in these nodes of this RAM architecture, then there are exponentially lots of occasions where error can happen in access to this quantum random access memory, and that means that you have very high expectation on fault tolerance of this device. The other reason that maybe this is not super appealing is that if you look at a fair classical counterpart to what a quantum RAM data structure looks like a data structure that you would use to access through QRAM, then you would have methods for dequantizing algorithms, in the sense that then, if you have that kind of access to classical data without the QRAM in a classical architecture, then there you can also achieve exponential speedups for these tasks. So maybe it's just too strong to assume that we can access data in QRAM. And this work is known as dequantization, and started from this 2019 paper from Evan Tang, who first dequantized this quantum recommender system, but then it turned out similar techniques can be used to dequantize all these other quantum and machine learning algorithms as well. Okay, so if the machine is quantum and the data is classical, and that's where I'm interested in finding good schemes, then the story is more challenging in a way. So as I said, there are two components to machine learning schemes. So there's this model, there's this graphical model, and then there's this training method of that graphical model. Okay, so there are lots of QML proposals and different publications in the literature where they focus on turning this graphical model to a quantum graphical model. For example, a neural network, you implement it on GPUs, for example, that's a circuit, that's a classical circuit. The weights and biases of the network become instructions in that circuit. So it's a classical logical circuit, and what it does depends on the choices of weights and biases in your neural network. But a quantum circuit is also a circuit, and it comes with parameters. For example, rotation angles of qubits, or like how you couple the qubits to each other. So entangling gates, you can parameterize a quantum circuit as well. And then you get a parameterized graphical model, but this time it's parameterized quantum graphical model. And there are lots of places where this kind of approach has been used. I've also used it to try to find places where you can see advantage from using quantum computing for learning schemes. One of those places, and most of these algorithms rely on what is called variational or hybrid quantum algorithms, or NISQ algorithms. And what NISQ is, it stands for Noisy Intermediate Scale Quantum. And this became like an interesting problem and a focus of the field for the past few years to, now that we do have these small scale prototypes of quantum devices, but they're noisy, they're not fault tolerant, can we find good applications of them? And one of those places that people have been looking for an application it's been in learning schemes. So variational algorithms were also proposed for solving for quantum chemistry applications, for studying lattice gauge theories and so on, and generally thinking of this circuit as parameterized circuit. And then you have a scheme, you have an outer loop with a classical decision-making scheme, like a classical optimizer that tries to, you start from one quantum circuit, you look at whether that quantum circuit is doing its job. For example, is it predicting dogs versus cats well? And if it's not, then you use that to update the quantum instructions that build the circuit. This is the scheme that has been studied really well in the past few years. And there are certain caveats to it. So it doesn't have that quantum RAM problem anymore, because the data set is it's one at a time. It's kind of this online setting of receiving training samples, which is great. The classical optimizer out here, however, has this problem that you might have heard of backpropagation in classical machine learning, and that's a gradient-based method of training classical neural networks. But if you try to do something like that using these quantum circuits, a problem that arises is it's not exactly like vanishing gradient problem in recurrent neural networks and deep neural networks, but that the gradients are small. Just it's not a result of backpropagation that they shrink or blow up in scale, but that just because it's this quantum landscape that you're exploring, the gradients are very small, and then this is known as this barren plateau problem. So that means that you have very noisy gradient estimation. You have to do this, you have to repeat this circuit exponentially many times to get good kind of signal to noise ratio to be able to train your scheme. The other maybe objection about this approach is that a machine learning scientist did not ask for a better representation, a better graphical model. In fact, the simplest classical graphical models have a lot of expressive power. For example, we know that restricted Boltzmann machines are universal. Okay, you might need to use exponentially many hidden nodes, but we have a lot of universality results about classical machine learning schemes. So both, kernel methods and things that look like undirected graphical models like Boltzmann machines, all of these have this universality in them. So what does it even, why would you even go from that classical probabilistic graphical model to a quantum variant of it? What are we supposed to achieve? And that's one of the questions that the field is studying these days. Okay, so now I want to pick up where I left off with saying, let's see what the machine learning scientist actually needs and look at their wish list and see if we can make quantum computing have an impact in those places. So there are lots of challenges to deep learning. Deep learning has been successful a lot, but there are also lots of places that it seems like we're now hitting the edges of what we can do with deep learning. For example, one of them is that our methods are very sample inefficient. So you have to show millions and millions of faces or millions of trials of interaction of a reinforcement learning agent with environment until it learns something. And that's really not how biological neural systems learn. I mean, the first time that a human infant touches, fire, they would not do that again. Just the learning you make from that one sample is good enough so that you don't repeat that. But if this was a reinforcement learning agent, it's doomed to burn its hand for years and years to come before it learns to not do that and find a policy that avoids that. So sample inefficiency is a big problem. Like image processing data sets, even CFAR10, CFAR100, and you get to these high resolution face recognition data sets these days. They're like in tens of gigabytes. If you want to learn faces, you show, in fact, the same face from so many different angles, so many different backgrounds. If you're trying to do something like reinforcement learning, this really nice achievement from reinforcement learning, which is amazing, that we can now train a robotic arm to manipulate a Rubik's cube. But the training for that has gone through making sure that, you're not picking up a pattern that is specific to a purple color of the hand or a specific color of the background. So you're trying to show so many data points so that you kind of average out these things that the agent is not supposed to try to pick on as a pattern. And that makes your learning scheme very, very expensive. So the original Atari 57 benchmarks that were done in DeepMind, they used as far as I understood, something like 83 hours of simulations of the Atari games. And you should compare that to how long does it take for someone to pick up an Atari game. I mean, even without getting an explanation of what the game is. The AlphaStar benchmark for reinforcement learning had 200 years of simulations. This Rubik's Cube from OpenAI had the equivalent of 10,000 years of simulation. So this is clearly not how biological intelligence is learning. There are other problems. For example, just the fact that you have this a very slow and sample inefficient scheme makes you use a lot of power for training. So that same benchmark used about 3 hours energy that is produced by an entire nuclear plant. If you want to get our natural language processing performance from about 10% error that is state of the art to half that error to 5% error, then you have to, it's really just an economical decision. Are we going to spend, are we going to spend as much electricity as New York City does in an entire month? And that's the amount of electricity we have to spend in our data centers to improve the NLP model from this 10% error to 5% error. Okay, so there are other problems that are maybe discussed more frequently. For example, it's not like, what if I can't trust the decisions that the agent is making? So what if, what this interpretability of the results is a problem? And people tried to study interpretability, and then they came up with other anomalies for deep learning. For example, the assumption was that, if you're learning this panda image, things that look like the panda image should also be classified as a panda. But then the adversarial attack paper, the original one by Kutfala and colleagues, showed that, actually that's not the case. Like, you can add very small perturbations of that image. So this one looks completely like the first image to us, but the predictor, the machine learning agent would now actually very confidently, 99% confidence, classify it as a given instead of the 57% panda of the original image. And then you can see how this could be concerning. So you can like, in a recognition, in the face recognition scenario, you can completely fool the system. If you're making a automated like radiologist, which is one of the technologies that is very very interesting and being deployed these days, you can create attacks on that system that takes a normal X-ray picture and then classifies it as abnormal, or like a classifier for tumors. You can make it fool it with showing a benign tumor as a malignant tumor. Okay, so and then this area of adversarial attacks was developed way more later on. But maybe it's like the image, maybe it's the digital image that you can do that attack on. But then this paper was actually printing off the attacks and then showing that even when you print off the attack and then scan the paper that you printed the attack on, you still can create adversarial attacks. Maybe it's like only when you add noise, like on the entire image, but this stickers that are adversarial attacks. So it's not changing the banana itself, but just put the sticker beside it, and then you can completely ditch classification. And then you can see in real world, this can be a big concern. Like, what if your stop sign is read as, 100 kilometers by your automated driving scheme? Or, in surveillance, you can make like adversarial accessories that you can wear, like wearables that you can ditch classification with. Okay, so in this last few minutes, I want to present the scheme that is kind of work in progress that I'm doing, and maybe we can find better schemes of addressing these caveats of deep learning, but they might have a expensive computational subroutine that we can then do on a quantum computer. So one of these places is what's called energy-based models. So energy-based models, they are also a graphical model, and then you associate a model distribution to it. But the only difference is that I actually don't have access to the distribution. I have access to an unnormalized, I have access to this distribution up to some scalar, and I don't know that scalar value. So these are called unnormalized graphical models as well. So, for example, and the distribution is usually written as exponential of some energy potential, so minus energy function, and then the model is representing this energy function. But if I wanted to understand the probability distribution function, I have to sum up all these exponentials over all choices of x, and then divide this number by that. That's this normalizing constant that then turns these numbers to actually as if they were coming from a probability distribution. And just the fact that I don't know that constant gives me so much flexibility in the machine learning scheme. So this normalizing constant in statistical physics is called the partition function. And it's also a holy grail of quantum simulation and just physics simulations, that if we could know partition functions of physical systems, not just quantum ones, then we would know a lot more about their physics. So just the fact that we don't know the partition function gives us a lot of flexibility in these energy-based models. But the training scheme for them somehow needs me to have access, obviously, to the distribution somehow. So you don't directly need to know the partition function. If you did, then you have an efficient scheme. But if you don't, then you need to be able to get statistics from the model according to that probability distribution function. So this means in the physics language, it means I have to be able to prepare what is called the Gibbs state of the model. And then I have to be able to ask questions about that Gibbs state. So these are called observables in physics. And so if I could efficiently find observables of the Gibbs state of the energy-based model, then I have an efficient gradient-based method for training it. Okay, so then there are questions. So do energy-based models improve the representation of data? And then can quantum computation help with the intractability problem of training energy-based models? And I've, so in modern energy-based models, so energy-based models were studied at a time where, at the winter of AI, before GPUs enabled us to train very large deep neural networks very well. In fact, people were looking at energy-based models back then, but they were training very small ones. So, for example, restricted Boltzmann machines, Hopfield neural networks, general Boltzmann machines, deep belief networks. All of them are energy-based models, but they kind of were set aside after GPUs just made it possible to train deep learning in scale. But there is now a new kind of reincarnation of these energy-based models, and now they're state-of-the-art as generative models. So, now the graphical model is not these early days kind of energy-based functions like Boltzmann machines, but they're actually large deep neural networks like ResNet, whatever you use in your vision task in deep learning, and then you just change the loss function of your scheme from what was this likelihood training to something that depends on an energy function. But how can we, I just said that, Gibbs sampling is intractable. So how are people training these more modern energy-based models? And the answer is you kind of use the differentiable programming that's available in GPU, and you kind of try to work around Gibbs sampling by simulating something like stochastic Langeveldt dynamics, but you do it for very, very few iterations. It's kind of numerically not very stable. So the technology at this point is good enough so that we can write papers that show their merits to be able to train these schemes, but is not stable enough that could be commodity machine learning approach. But these literature that are training these modern energy-based models actually have claimed that there are improvements in the representation of data. For example, the model that the representation you end up with is much more adversarially robust. It's more robust to adversarial attacks, or it's more calibrated. So calibration means that I have the accuracy of my model, and then there's a question of maybe I did find cat versus dog, but I wasn't very certain that it was a cat. So that's the confidence. And then what you want from the agents and decisions is that the places that you're not very accurate, you should hopefully also not be very confident, because if that's the case, if your model is calibrated, then for example, that automated radiologist can look at the easy X-rays and then take care of those without involving the human radiologist. But then the places that it's uncertain, then defer those to a human domain expert. So for that scheme to work well in a sensitive decision-making scenario, you want a calibrated representation so that the places you're not confident are also the places your accuracy is low. Okay, so it seems that what is being told in these recent literature on energy-based model is that you do actually get a more calibrated representation, more robust representation. And so I earlier, a few years ago, I started working on like, what if we use those early days kind of energy-based models and then try to do Gibbs sampling from them using a quantum computer. And this is just repeating what that training scheme looks like. And I wrote these couple of papers with my group on building a reinforcement learning agent using what was called a quantum Boltzmann machine. And we were showing that for these very small tasks, in fact, the quantum Boltzmann machine is more efficient to train. So these two lines are kind of those quantum variants, and then this brown one is the classical Boltzmann machine. The problem is it's really hard to test these on larger. I mean, unless I have a large quantum device to test these things on, it's really hard to predict how this is going to scale when you go to larger tasks. So this was a very simple, solve a small maze problem, but I wouldn't be able to predict how things will go if we were to do this in larger data. And so what I'm trying to do these days is to find schemes where I can find a theoretical guarantee for the performance, and use what is theoretically known about efficiency of Gibbs sampling in quantum computers, and use that to build schemes for machine learning. I'm just going to skip this one slide and then show you guys this quick schematic from one of the papers that I wrote with my group, where here we are using a deep neural network, but we are then composing it with a graphical model. And then this graphical model requires Gibbs sampling. So we do Gibbs sampling here, and then we back propagate as if you did it in the classical setting. And the nice thing about this kind of setting is that, again, as I said, I can find like theoretical guarantees for a convergence rate. I know what exactly the quantum speedup would look like. And I can analyze this theoretically, even though we don't have those large-scale quantum computers available today. So then the question that now I'm trying to address, and this is a work in progress with my students and my colleagues in 1QBit as well, is how can we find workarounds using quantum computing for this expensive thing that I said is stochastic Langeable dynamics. So as you see, these are benchmark results for like generative models that were built using energy-based schemes, and they do achieve like state-of-the-art generative measures like intersection score, other if you turn it into a discriminator to have a state-of-the-art accuracy in prediction, and that is achieved. But then the question is, can we now build good quantum Gibbs samplers for this modern kind of approach to energy-based learning? And I think I'll just summarize quickly that, so designing quantum algorithms is challenging. On one hand, you have the quantum features of the computing scheme. They kind of work against each other. So the fact that you can create these exponentially, you can create a quantum state with exponential lots of information in it, is kind of making it so that you have a quantum advantage. But then, for example, the fact that measurement makes you go from you only get access to information about your state at a classical single bit rate, in a way that it works against that quantum advantage. So it's challenging to design good quantum algorithms. There are many proposals for how we would want to use them for machine learning tasks. Unfortunately, the numerical studies don't provide evidence because we don't have access to, the same way the way the paradigm in classical machine learning goes is that you there was a data set, there was a vision task that was not done before, and here it is, we have done it now. And we're not in that situation with quantum computing to be able to actually unlock a new computing task. So the question is, like, how do we, numerical studies will not show us the scaling of the method at the industry scale applications. But then the theoretical results that exist are mostly about these assumptions, for example, existence of QRAM. So it's quite challenging to make a dent in a scenario that is guaranteed to provide a quantum advantage. So I'm hoping that, really going back to what quantum computers are supposed to be used for, which is like simulate quantum mechanics, Hamiltonian simulation, like simulate quantum evolution, would give us a path to find the right kind of, put the pieces of the puzzle correctly together so that we actually get a viable, with theoretical guarantee, but we also know what type of quantum computer we have to build for it. And we know exactly where that advantage is going to be for machine learning tasks on classical data. So this Hamiltonian simulation could provide, a path to break that curse of dimensionality for these energy-based models. In fact, if that happens and we have partial results on it these days, if that is the case, then I can now look at the cases where, for example, that condition number in the linear system solver that I said, and find graphical models. They might be just classical graphical models, but they might look different from deep neural networks, or like skip connections in resonance, or convolutional units and recurrent units. All these architectures were built by exploring classical tasks using classical graphical models. Looking at the performance of these other schemes would let us maybe build new architectures that work better with these quantum training schemes. Okay, and the reason I hope that this is useful is that it might give us the same way that energy-based models are giving us improved representation of data. Then we're looking for quantum algorithms that can achieve the same. So it might be that the training is more efficient. For example, you build quantum algorithms that do convex optimization better than stochastic gradient descent, or it might be that you have an improved representation of data. For example, you have a more calibrated representation or a more adversarial robust representation. And these quantum algorithms are not going to be NISQ algorithms. They're going to need very, very many gates. And so that definitely requires fault tolerance. And then the question is how much fault tolerance we would have to have in our device. For example, what type of error correcting codes we have to use, what quality of measurements or what quality of gates we have to have. And those are things that we can analyze by designing these quantum algorithms, and we can completely, before building those devices, completely predict what are the performance parameters of that quantum computer before we go ahead and build it. And with that, thank you for listening.
Thank you, Pooya, for joining us today and for a very comprehensive overview of a topic. You made it so accessible and understandable. I have two quick questions, if I may. And going back to your very interesting paper on finding the ground state of spin Hamiltonians, you talk about controlled online optimization learning. Now, you used proximal policy optimization, which is already an improvement over trust region policy optimization or actor critic with experience replay. But since then, there have been proposals, for instance, of trust region guided proximal policy optimization, where, for instance, if we don't initialize in PPO right, then it can get stuck in sort of a local minima, or it cannot possibly converge. So is future work perhaps going back to that work on COOL and perhaps swapping out some of the RL algorithm under the hood?
Yeah, that actually is a very good question. Yes, we kind of took PPO as our off-the-shelf state-of-the-art at the time. And you're definitely right that the field has improved a lot since then, and we only looked at a very simple task. So we were looking at spin Hamiltonians, and we were looking at ground state preparation, but and we were looking at the Sherrington-Kirkpatrick model at the time with +-1 couplers. But if you make that quantum task more complicated, then there's a good chance that PPO would not cut it to be able to find the right policy. And I think that's a very, very good avenue of future research of, try to do the same kind of approach for more complicated quantum evolutions, classical or quantum evolutions, with more state-of-the-art reinforcement learning. I think that's a very, very interesting avenue of research.
Absolutely, Pooya. And, from my perspective, I'm thinking even a comparative analysis where we look at it from a cost-benefit and a price-performance perspective too, where eventually they might all converge, but perhaps one policy is more numerically stable than the other, one policy converges faster, et cetera, et cetera. So that would be, I'd love to read that paper as well. Another question that comes up is, one of the areas where there have been quite a few advances in reinforcement learning, Pooya, as is in multi-agent reinforcement learning. And one of the areas I follow with keen interest is sort of looking at the Ising model and then seeing, for instance, mean field approximation, mean field Q learning, mean field with some of the other approaches out there. So would you see perhaps an opportunity to take a multi-agent reinforcement learning view to solve the problem of finding ground state of spin Hamiltonians?
Yeah, I mean, that's also a very interesting point. I haven't thought about it, but now I'm just like thinking out loud. I think that, one of the things that we had to do in that paper was to run multiple simulations at the same time. Because what the reinforcement learning agent was supposed to pick up on was whether you are in this, frozen parts of the dynamics. And if you're in that frozen segment of dynamic, then you have to heat up the system so that, you get more, you kind of introduce more entropy in the system before you cool down again. And the goal was to, gather statistics, not really just one set of measurements of the system. And so the way we did this at the time was we took replicas of the same, like we independently were running multiple experiments at the same time so that we can gather statistics of multiple runs instead of like relying on single observations. And I think that would be very, very interesting to explore in a multi-agent scenario.
Absolutely. You've got spatial aspects, you've got temporal aspects. And actually, it's great because that brought me to my third question, which is why I'm smiling, which was to do with approaches, right? So you talked about sort of gradient-free optimization. And one of the things is population-based training, where exactly what you just said, where we have independent agents. And I think that's also where we can take sort of some of the computational speed-ups from doing population-based training. And then we use a multi-agent reinforcement learning approach to get to those models which don't get stuck in sort of suboptima or local optima, etc. But maybe that's a conversation worth a coffee, or the next time you are back at the
Absolutely.
Synthetic Intelligence Forum, you'd be kind enough to share advances in this line of research, but also some of your most excellent line of work around GANs. But for this one, I would like to thank you, Pooya, again for being so generous with your time, and look forward to having you back in the forum very soon.
Thanks for having me.
Thank you, Pooya. Bye for now.
Bye-bye.